So we'll do one more topic, and that is that of functional diagrams. Okay, so functional diagrams are a way to represent a system in an abstract way, but still helps us understand what the general structure of the system would be like, right? So it's a block diagram representation. You take blocks. NASA has been doing it for a long time. A lot of companies do functional diagrams, and then they mean different things, slightly different things, but the general idea is the same. As a block diagrams, where roughly each component is a block. Okay, and then you see how different things flow through them, through each component to other component, and so on and so forth. Okay, so how the different elements of the product, roughly components, are functionally connected, right? So they don't, even at functional diagram stage, we don't think of specific design implementations because we want to have as many ideas as possible on how to address the same need. And we'll talk about this in a little detail in a bit. So they're not unique. You should not think of specific design implementations. They help understand workings of products so that brainstorming or other concept generation ideas can be used so that you come up with more innovative designs. Okay, so they're not unique. If I draw a functional diagram, you draw a functional diagram, they draw a functional diagram, it may be different. Okay, so long as you address all the customer need and I address all the customer need, we're good. And it is a good idea to generate quite a few different ones if it helps you generate new ideas on how to make the product. Okay, another thing to keep in mind, the decomposition is along functional lines, right? So don't think physical decomposition that you can say that, oh, there's a hinge here in this laptop, so you have the base and you have the screen. That's the physical interface. But you should not forget that yes, there's a data cable going from the bottom to the screen, and then the sensor, which is a touchscreen laptop, that is sending signals back to the base, right? So there's other connections going on than just physical. So we're more interested in functional connections than just physical connections. And in functional diagrams, we make sure that each block that we draw accomplishes a specific task or subtask, and it's a separate entity, right? And then we connect these with flows. So these are connected to flows because all products, I don't care what it is, accept, store, generate or propagate energy. Even when you're using a peeler, as simple as you can get, it's taking energy from your hand and using it to separate layers of cells from the vegetable. Okay. Another flow is usually material. Like, if you have a stapler, staples come out, right? Have you had a stapler that works indefinitely without adding staples? No. Right? Have you had a stapler that works without no force? No. You need those things to flow through the system in the right way. And components will transform, modify energy, so that they can be used by components downstream or output from the system. So if I have an energy, somewhere, whole functional diagram of this webcam activated, and some energy will be sent to the LED next to the camera saying, hey, your camera is on, right? So that energy is released to the user to detect. Okay, so stapler, I intentionally keep changing the products on you so that you don't get bored. But hopefully you can see this, but you'll get the slides from me. I heard that somebody was requesting slides, so I can send you the slides too. Okay, so
So what would be the functional part? How do I represent safety? Because it's not the function, right? It is more like performance.
I don't think you could. The way you're thinking, no, yeah, I don't think you could. I mean, unless, I have an example for that, okay? It cannot be explicitly safety. It has to be something that broken down into safety. Actually, let me just go through the slides. Actually, we'll do the next half, okay? So basically, I'll give you a brief example, just a spoiler. There's a system that collects fluid, and then it becomes more and more acidic. So we have sensors that sense the pH of the thing, and then it outputs an alarm. Okay, so not safety per se. I don't think you could do safety per se because safety doesn't flow. But you could say something that implements safety is this alarm that does the pH sensor output. Okay, so just to help you out, there's energy. It could come from hand, right? So there's two kinds of flows. There's a solid line here and a dotted line here. The solid line is material flow and the dotted line is energy flow. So the solid, apologize for the small font. So the top line is dotted, and all this energy is flowing to multiple of these boxes, right? So there's staple extraction, which is somewhere something has to, you put a whole cartridge of staples in there, something has to extract one to use it, right? So if you've actually opened up a staple, there's actually a basically a metal plate that pushes a staple. That extraction takes energy because it is glued together. It has to be separated, right? So when you press the staple, your energy is actually going to multiple places. One is extracting the staple. The other one is paper and staple alignment. You cannot just say, here, staple this. No, you make sure it's aligned. So energy is going into aligning the paper, and then paper being stapled also takes energy. When you actually punch and it goes through and bends the other side, that takes energy too. And then readying the next staple. Okay, so that goes out, the plate comes back out, and the spring pushes it forward. Okay, and then finally, material. So staples are and papers are the materials. Paper goes in. Staples go in. They have to be stored somewhere. They get extracted. They are aligned. Paper, staple, staple, papers. Papers will be stapled paper, and then it goes there. So that's the one area where all this thing is happening. In the top row of blocks, we have a paper and staple alignment. In the middle one, where you have a whole bunch of things going in and a whole bunch of things coming out, that's where all the things come together, and then papers are stapled, and then they're output. So I guess I had these marks to.
So when you put too much of energy, there are so many instances where you put too much of energy and the paper and staple is not connected.
Okay, great. Okay, so we're going to take a 15-minute break and then we'll come back to this discussion. That's a very good discussion, yes. All right, so let's get started for our second session. So we had a few discussions that we started before we took the break about this functional diagram. So quite a few questions came up. So functional diagrams are not unique in that somebody else could think of a staple and come up with a different design, and that's fine, so long as you address all the needs. Functional diagrams also do not have to have so much detail that you get overwhelmed. Sometimes keeping it abstract helps you with different designs. And actually, I can show you what different designs, at least a hint of how different designs can be realized just by looking at functional diagrams differently. And many times what we would do is we would hone in on one of the blocks. Okay, so we'll look at one block and look at what sort of inputs are going in, what sort of inputs are going out, and just design that module. Right? And that's, so if we have a design already done, we can say if we take this module and replace it with some other module, which takes the same inputs and provides the same output in a better, faster way, then that's better, right? So functional diagrams have that utility. So aside from affording clarity, right, I think that it was eye-opening for me when I started looking at functional diagrams. I could make anything, right? I felt like everything's a black box, right? How's this made? How's this table made? How's the computer made? Pretty much once you have the whole idea of how systems are developed and customer needs to stuff, things start making sense. And of course, I strongly recommend develop a habit of dissecting products. Okay, we have something that you no longer use, open it up, see how it's assembled, what different parts are there, and things like that. So being hands-on is very important for engineering. Okay, so the biggest thing the functional diagram does is it helps with concept generation, right? So you have the customer needs, you have the functional diagrams, and you start conceptualizing how roughly the product is going to look, or the system is going to look, what are the different flows in the system. Now you can actually start thinking of actual solutions to those problems. Okay, so now this is sort of a definition. Concepts are technologies or working principles that will be utilized for component implementation, right? So working principles. It's like saying that I will use electromagnetic force to staple. Okay, so electric staplers, that's what they do. They have electromagnet that has a plunger and then goes like that. Right? For example, we will ready the next staple with the help of a spring. We will use an electric motor to create relative motion between the vegetable and the cutting edge, right? So if you want to make an electric peeler, you say, okay, how can we make an automatic peeler? That's great. And then we'll return to these discussions later in the course, and even some of this would be referred to later in this lecture itself. So now this was one way of customer preference, right? So I will come back to concept generation, but we talked about customer needs and all that. This was telling me the specifics of what is it that they want out of a product and how the manufacturer or the designer can go about designing or manufacturing it, right? That's one way to think about customer needs. The other way to think about customer requirements is that will anybody buy it? Okay, that's a more, I would say, more marketing type mindset of how we should design products. So think of it this way: customer wants this, I make it, but there's millions of customers, right? So how do I make something that millions of customers, or at least some large portion of them, will buy? So now I have to start thinking about demand. And some people have actually came up with a holistic model where they say that, okay, I can have a demand model that I assessed. The demand model is a function of, takes product attributes as inputs, and product attributes are outputs of my system model. So I can do this whole optimization so that my market share or my profit is maximized. People claim that you can do that, right? So let's spend some time talking about product demand and how we can products and systems for considering the demand of such products. Okay. So people always say, should we make the most reliable product? What's the risk with that? Now this time our context is we want to sell it to many people. Make it most reliable. That's a good thing. Nobody can say reliability. Cost will go up, right? And sometimes reliable is not necessarily it. Some old reliable things are considered outdated and people don't buy it because it's not fun, right? Good for society, right? This is really great. Well, again, usually comes with cost, or we talked about stated versus revealed preferences. People don't always want to spend money on something that is good for the society. They will say they will spend money, but sometimes they don't. Or one that makes the most money. Like I said, that's why people tie it to demand. That's why people say money is not necessarily evil in this context, as I've said many times. This is commonly accepted in engineering design community. People say, come up with a demand model, tie it to your design model, and then design something that has the highest probability of selling, ergo chances of making the most money. Okay. What is the challenge with this? How do you make a product that sells the most or makes you the most money? We may not explore new technologies, or we may explore new technologies if we think it's going to get us more sales, right? I mean, a lot of companies innovate just so that they can stay ahead of the competition. So that's one possibility, but people say, give me a demand model. I challenge anybody to give me a demand model that works, right? We usually fit data to past purchases. A lot of products that we have are changing and evolving every day. So our past demand models may not work for the future. And even if they work for today and future, they may not continue to work in the future. So we don't have a good demand model, ideally. Even though it's a great concept, we generally we cannot translate. Number one, we cannot always have an exact model of the system performance and how it maps to system design that maps to system performance, ergo the attributes. And we don't always have a good model of the demand, right? What exacerbates this is the fact that you're not the only people who are making stuff. Other companies are making it too. You're competing with people, right? So you may not be able to sell as much as you think you will. So the challenge with trying to convert everything to money is, it sounds good, mathematics will make sense, but we don't have good models that we can rely on all the time. Okay? So a product is a bundle of attributes. So that's a statement that people say, that a product can be thought of. You can say that this is a bottle, but then you can also say this is a bundle of attributes, as in this is something which is about a foot long, about 3 inches in diameter, made of stainless steel, holds 1 liter of water, has this much heat. So I can just write down those things and I have described it, right? Because that's what the customer cares about. I can even talk about, there's even ways of encoding shapes of products because people prefer certain shapes to others, right? If this water bottle was this wide, I wouldn't be able to carry it comfortably. So it's a bundle of attributes, bundle of different measurable things that define it reasonably, okay? So once we start thinking of products as a bundle of attributes, then we start thinking of trade-offs, okay? That every decision that you make is a trade-off between multiple competing attributes. And a common way to show this is through using a Pareto front, okay? So here we have a graph where we have x-axis is attribute 1 and y-axis is attribute 2, okay? So 2 attributes. Think of it anything like cost and power, or capacity versus weight, or something like that, right? So, of course, there could be many, many attributes. Here we're just showing 2 because it's easy to show on a 2-dimensional surface. So, the general convention is, which we often violate, is that the origin is the utopia point, as they say, is the best point. Means that attribute 1 is such that we want to minimize it. Attribute 2 is also something that we want to minimize it, okay? So it could be weight and cost. We want to minimize cost, we want to minimize weight, okay? And it doesn't take away from generality, because even if it's something that you want to maximize, let's say power, you can just reverse the axis and somehow visually you can still show it at the origin. So it's not even a problem, okay? So let's say I have a product here that has a certain level of attribute 1 and attribute 2, right? To be able to say how much we're going to sell of this, we should be able to find out how much this will sell in the market, right? This attribute level, this attribute level. And again, products are bundles of attributes. A system is a bundle of attributes, okay? Means that I can convert them into a bunch of numbers like this, okay? Except that I don't just have one product or system. I have multiple competing products in the marketplace, right? I have to think about product placement. I can sell something that is really high on attribute 1, the bottom right, and really low on attribute 2, and the top left, which is really low on attribute 1 but really high on attribute 2, and anywhere in between, okay? So of course we have to think about where we want to place this. You don't want your own products cannibalizing the sales of each other, but you also don't want to have too many gaps, or other competitors will come and take that spot, right? And of course you don't want to have dominance, right? So this product will not sell, or should not sell, I should say, because it is, look at the third dot from the left, right? It is worse on attribute 1 and worse on attribute 2. Another way of saying that it costs more and it performs poorly. So why would anybody buy this, right? So you don't want to have those kinds of things. It's called dominance, and we'll cover this quite a bit in multi-attribute decision-making part of the course, okay? So no need to panic too much at this point. But the whole idea is that this general concept helps, that you have attributes. Products are bundles of attributes, and then the offerings that you have and then in the market should be such that every product and every other product is some sort of a trade-off. You cannot say this is better on all attributes, then that will sell, this won't. But if you say in some attributes this is better, some attributes this is better, that's when you get a parade of fun type situation. Not to say that it doesn't happen. I mean, I've seen certain cars that I say, you know what, that car is better at every attribute that I can think of, and is cheaper. Okay, and then you have competitors. You have your own products and somebody else. So the challenge with demand modeling is not that, which is what I was trying to allude to earlier. People would say, okay, you should have a demand model that you couple it with your design model, and then you should be able to predict how much money you're going to be able to make. Well, yeah, try doing it for a marketplace that looks like that, and then we'll talk. Okay, so then you have relative demand of your products and relative demand of your products versus other people's products, right? So it's a very complex scenario. Of course, in theory, everything works. In practice, a lot of these things don't work, right? So that's why we have to be pragmatic about how we think about demand. But nonetheless, we should understand fundamental demand modeling methods so that we can at least make back-of-the-envelope type calculations. Okay, so demand modeling is the use of statistical methods and forecasts to predict the sales of a product or a system. Nothing to really explain there. So there's two things I say about, in the initial stages, I think that demand determines feasibility. Okay. In the initial stages, before you start even conceptualizing, you think about maybe I'll build something, and maybe there's a need for a new jet engine or something like that. You should think about, okay, well, how many aircraft manufacturers are there? How many people will buy engines? And you say, you know what I'm offering is not going to make me any money, so it's not even feasible, right? So it's the first rough cut analysis of what is it that you should be trying to do with your design. So demand determines feasibility. Is it even worth trying? And then demand determines optimality, in the sense that if you have good models and maximize profit, and you solve your objective optimization problem, then you can even talk about demand as an optimality. Remember, I said if you have all these good models, then yeah, the optimal design is the one that makes you the most money. So two things: demand determines feasibility in initial stages, but demand also determines optimality of your product, whether it's a good product to make, it's a feasible product to make, will customers buy it, and will it make you profit? So first things first, a very, very simplistic way of looking at things. How would you find the demand or market size of a simple household product in a given city?
So based on the population,
Mm-hmm.
based on the particular population.
Okay.
Like the city where the population will be more,
Right.
we will be having a greater market size.
Right. But let's say I give you the market size for a microwave. Excuse me.
So it depends. Maybe it depends on the lifestyle of the people. People where it depends on the lifestyle of the people. It could be a city where people wish to have ready-made foods which will be easily which can be easily cooked. Or for example, frying a fish in an oven, it takes less time than making it in a pan. So, or it could be something that could be easily cooked. And even microwave ovens have feature they have the recipes inbuilt in the microwave oven, so they don't have to much think of it what to make and how to make it. It's already they have the recipes functioned in it. So they just have to put the ingredients into the oven and set the oven in such a way that they get that particular recipe out of it.
Okay, so all you're saying is that offers advantages over conventional cooking techniques in certain cases, right?
Yes, sir.
Okay, so that's a great start. So let's say if you have a city of, let's say, 1 million people,
Yes.
you can start coming down to, well, in a house, not everybody's going to buy a microwave oven. One
Yes.
person,
Yes.
one household will have one, let's say,
Yes.
or at least in the best case scenario. Then you say, okay, well, average household has 5 people or 6 people or something like that.
Okay.
So 1 million divided by 6.
Yeah.
Right? Then you say, okay, well, I know that general penetration of microwaves in a, let's say, place like where we are at right now is such percentage. And then you have a factor attached to that. And then you say, well, once you buy it, you're not going to buy it for another 10 years, let's say. You know the average lifespan of this. So you divide that, okay, it's so many per year. So that's one simple, rough cut way
Yes.
of coming up with generally how many units you will be able to sell in a year, right?
Yes.
And then you obviously take into account like how many will buy competitors' products, how many will buy. So you have total population, number of households, how many would they buy per year, what percentage people would buy it, what percentage will buy your product, and you can actually use discounting factors using discussions, or you're allowed to do research. You can find data, and then you can come up with a very simple way of finding how many of it you're going to sell. So when I said in one of the earlier slides that demand determines feasibility, you can make these kinds of feasibility type analyses. This is not going to be a very good, accurate analysis, but it gives you an idea. You know what? I can sell about 2,000 a year or something like that. You come with a number like that, and then start from there. Maybe it's worth pursuing this design or not. Okay. So that's something you can play around with for most cities, and you'll be surprised because a lot of these things cancel out, and you say, oh, you know what? I was able to find so many of these will sell in a year, and then once you look at the numbers, oh, that was actually pretty close. Or if it's not, you'll think about, okay, I missed a factor that I should have used. Okay. Okay. Now, another thing that you might be familiar with is the demand curve and demand elasticity, right? Which is defined as a percentage change in demand divided by the percentage change in the attribute, right? So you can, here's a graph, let's say price and demand, and then price increases. Typically, demand goes down. We talk about elasticity because we want to understand, like, okay, a product sits somewhere in the attribute space, okay? I've always talked about having scalable preferences, right? Scalability means that I can move things around and still make some deductions. I'm not just stuck with that number. So what will happen if I made it more expensive? I mean, I'm sure you've seen in markets, some people will sell high-end products, but then will sell it at a really high price because they think that they can pull more profit that way by selling fewer units at a higher price. Other people will say I can sell more units at a cheaper price. So they have to know what is the elasticity of demand to price. You can have elasticity of demand to other attributes as well, right? So you could have attribute elasticity to, in a car, you could have, cubic feet of space, miles per gallon, so on and so forth. So why do you think we define it as a ratio of fractions? We never say change in demand over change in price. We say percentage change in demand versus percentage change in price.
The existing scenario.
Right, but the thing is that we just want to make it unitless, right? Okay, so that way, if it's percentage here, there's no units. So now you can compare elasticity over different attributes, right? It just makes it unitless. What is the sign of elasticity? Depends on the attribute, right? So it could be positive, it could be negative, right? Generally, price elasticity is
Like when the price increases, the demand will decrease,
right. So
like for the normal goods.
So it'll be negative, right? So these things are pretty much obvious, except in certain cases. Can you think of a counterexample to that? Yeah.
So there will be some goods wherein, like for example, when the income increases, the consumption reduces. Like in economics, we say that, for example, a person who is eating, for example, a bread made of maida or refined wheat flour will prefer bread made of multigrain or wheat when his salary increases, because that gives him more nutritional value.
Right. So I think that the gentleman in the back said it too, that for certain products it's actually negative. When there's luxury goods, usually people say that, you know what, the more the price, because people, for them, it's no longer about um, just having the product, it's also having the image of having that product, right? So they would say, you know what, more is better. And sometimes in times of shortage, that's also something we see. Suddenly the price goes up. And people, oh man, means that we're going to run out. And then more people start buying it, and then the price goes up. So I don't know which one's which, but I think it's Veblen and Giffen products. So you can look up those types of products. Those are rare examples, okay? Generally, price elasticity of demand is negative. For some products, for some other attributes, it could be negative. But it's good to know. So these are, I mean, of course, I am not somebody who works in marketing. I'm not a demand modeling guy. But I mean, you just know and be familiar with these concepts that they are, because we care about those as systems engineers, because like I said in the first lecture, everything is our problem, right? We have to look at the entire chain of things that happen from conception to being able to sell a product or a system and make money. Okay, so here's a brief example that I will not spend too much time on, because you all can do it, right? So it basically just says that they want to increase the cost of an equipment from 70,000. Something that costs 70,000 to produce, they want to increase the cost or the sale price from 100,000 to 110,000, but they know that it's going to decrease the sales. Okay, from 10 to 8. What is the price elasticity? It's pretty simple stuff, and then you can do the math, and then you'll find a number that is -2, and that's that. Okay. So of course we don't have to spend time doing problems like this. You can find examples like this many places in literature. Now, more interesting thing. So a couple of things to talk about is, like, if you have a rough cut, how would you come up with a rough cut estimate of how much of a product will sell? Okay, start with the population of a certain area, how many people buy, and then you get to a number that makes sense. And then we talk about elasticity. If you have a product, you want to change certain attributes and see how it's going to affect the demand. You can look at elasticity of the demand to those attributes. How would you collect that data? How would you know that, let's say you were selling microwave ovens at a certain price and you want to change some attribute of it? How will you know before you did it how it's going to affect your sales? Huh? You can do historical data. You can do surveys as well, right? And all the things we talked about initially, like revealed and stated preferences. People will say, "Oh yeah, I'll pay more for an extra feature," and then you realize that they don't want to pay more for extra feature. So yeah. The other thing that's also critical is relative demand, right? So in simplistic models, we say, okay, let's say we sell 1/5 of the products or something like that. There's a model that I think everybody should at least be familiar with, is what's called the logit model. So it's a well-known model to find relative demand of competing products, okay? So basically it says that each customer derives value from a product, which is the sum of two parts, the observed value and then the unobserved. So the observed is like, this function of attributes of the product. We observe it, we can see it, we can measure it. Other is some things we don't know. Of course, that's a good assumption, right? There's some things that the customer values that we don't know what it is, and we call it unobserved. So the observed part is function of the attributes of the products. The unobserved part is assumed to follow a distribution. Okay, so probability distribution. And So here you go. Now faced with an M alternative, so we're trying to talk about relative demand. If you have N competing products or systems or options available to you, I will prefer I over J in this case only if the value of the ith product is higher than the value of the jth product. That's as simple as it can get, right? Anybody have probability statistics here? You have probability statistics, right? So in the first line says that if there's uncertainty, that means that this is not comparing to constants, to real numbers. It's comparing to random variables, right? So random variables, we cannot say this is greater than that. We have to talk about probability of one random variable being greater than the other random variable, okay? Because in the first equation, V superscript T is a sum of deterministic plus a random component, which makes V superscript T a random variable. Ergo, we're comparing random variables. And now we say that we will buy an option only if it is better than all the other options, right? What is the probability of that happening, right? So we just say probability of V I being greater than J, and then you rewrite the expression going from the last slide. This derivation is all over the place, so you don't have to write it here, but just follow along with me, and then make some assumptions on the error terms, right? If the error terms are identically, independently, and identically distributed, D with Gumbel, certain type of distribution, then we say the probability that somebody will buy the ith product is E to that over the sum of all E to the values for all the competing products, okay? So like I said, you can find this derivation all over the place. Actually, Kenneth Train has a book on discrete choice. That's a very good resource for this this kind of analysis. But either way, it's pretty simple, right? So value function associated with a certain product, and then we calculate that for alternative I, and then you calculate that for all other alternatives, and then you just calculate the probability that somebody will buy the ith alternative. So it becomes very straightforward. And then if you notice, I don't know if you can, the superscripts here are just the observed parts, right? So the unobserved parts drop out in this analysis. Okay. So it has some, all models, as they say, all models are wrong, but some models are useful. Okay. So it has some properties. The choice probability is between 0 and 1. Great. Probability should always be between 0 and 1. If your model says the probability is greater than 1 or less than 0, your model is wrong. Choice probability cannot be 0. That's a bad thing, right? So that basically says that even if you have a terrible product, it'll still sell to some extent. Well, if you think that something is terrible, just don't include it in your consideration. That's what we say, okay? The choice probability follows an S curve as a function of value from an alternative. So what ends up happening is that initially when you increase the value, make the product better, you don't see an increase in the choice probability, which translates to demand, until you reach a certain point, then it takes off and then again levels out. Okay, so it follows an S curve, which we observe that it is true in many cases. And then the maximum rate of change of choice probability happens at 50%, which again makes sense, right? If your product is in the middle, you have the most to gain and you have the most to lose. If you screw up, you will lose a lot of demand, and if you improve, then you have a possibility of increasing your sales substantially too. Again, so it has a lot of good properties and it has a lot of limitations. If you're familiar with the limitations, and if you, then we are in a position to use it to our advantage. Okay. So basically, the text over there is telling you the same thing that I just told you, that products that are sold only in few numbers and products that are sold a lot, you can change things a little bit and it wouldn't change this sales quite a bit, because this could be because of brand loyalty, that only a few products sell, but then they sell consistently. Or if you sell a lot of that, okay. It's only when you're in the middle when you're at risk of losing market share or gaining a bigger market share. So another major property of logit model is called the independence of irrelevant alternatives. I'll talk about that in a bit. So, so what I have here is a brief example that we can all do at home. I mean, of course, it requires solving an optimization problem. But basically, the idea was that if you have, let's say, 50 customers that you survey, and then you come up with a few example products, and then you say how many will buy this, how many will buy that, how many will buy that. So going back to our original point, to collect data to fit any of these demand models, we have to perform surveys or look at past data, as you said. Okay, so here there's 4 choices: 1, 2, 3, 4. These are cell phones, different screen sizes, different battery life, different cost in hundreds of dollars. And then the survey of 50 people said that 20 people will buy that, 10 people will buy that, 5 people will buy this, and 15 people will buy option 4. We assume a functional form of this type, where say the value is beta 1 times S, which is the screen size, plus beta 2 times B, which is battery life, minus beta 3 times C, which is the cost, plus epsilon, which is the part that I don't know about. Use a negative in front of C because generally value goes down as C increases, cost increases, but we want battery life to be large and we want screen size to be large, generally. That's something that has fluctuated over the last 20 years. First, when cell phones came out, everyone wanted to make them smaller. And then suddenly everyone wanted to make them bigger. So anyway, so you solve for the best fit value function. You get these values with the beta parameters. And then you can make decisions like, if I go back here, based on this data, find the relative demand of A and B. I give you 2 things to compare. I now have a value function. I know the betas. I found the values of A and B, and I say that, relative expected demand is 61.4%, or choice probability, I should say. And then choice probability for B is 38.6%. Okay, so I have some hypothetical examples. I present them to customers in a survey. I get their responses that fit a demand function, and then I can now make predictions for other things that I'm trying to evaluate. Standard thing for everything that you do in engineering. Okay, so question for you. What if there is a new product in the market that takes up 50% of the market share? So we had A and B, now we added a C that we know took up 50% of the market share.
So A and B might look for the ways that they can increase their market share.
They could, but we're just limiting ourselves to the logit model. So logit model predicts what? If we said that we had A and B, A was taking what, 61% or something? Yeah, and then B was 38. What happens to these choice probabilities if C comes along and takes up 50%? Yes, but they will decrease, they will still maintain the same ratio as they were before, right? They were 61 to 38, they'll again be 61 to 38 after 50%, right? So sometimes that people say that is not a good thing, because the example people give is that if I, let's say, had 3 options to go to work, I could take the car, I could take the bus, or I could take the train, okay? Or let's put it this way, I could take the car, I could take the bus, okay? Suddenly, somebody introduces a train, what happens, right? I don't think the ratio of car to bus will remain the same, in my opinion. Earlier, let's say it was 50-50. When the train comes, it steals more from the bus than it does from the car, correct? Because public transport versus self-transport. So new competitors do not always take equally from all the existing products, right? So they don't always compete with and that's one limitation they say is of the logic model, that it maintains the ratio even if you add or remove products. So I gave you the counter example already. Other limitation, of course, like, we have independence assumptions, and best thing in engineering is always do sensitivity analysis, right? So change, what happens if my parameters change? Is my answer going to change? My prediction is going to change. One interesting result of sensitivity analysis is how to price the product. I have an idea. This is how much I think I can sell. Can I increase it? Can I decrease it? Those kinds of things. How much should I increase it? And that's the game that people are playing always. And a related concept, while we're thinking about demand, we should know there's two ways we can cost products, right? One is called the cost plus, and another is target costing. Anybody familiar with these terms? Yeah, so I can think like, okay, well, I'm making this, engine, and I take this much raw material, my electricity costs this much, my workers cost this much. Take my cost and I add a markup price or a profit margin or whatever, and I come up with how much I'm going to sell it for. That's one way to think about it. It's called cost plus. Okay, cost to manufacture product plus a profit margin. The approach is simple and intuitive, which is why it is so prevalent. It's so simple, it's straightforward, makes perfect sense, except it doesn't, right? So the problem with this is that it's oblivious to what the customers want. We were thinking about this whole lecture so far has been voice of the customer. What does the customer want? What do they want you to sell them? What is it they would buy? What's going to make you the most money? You didn't care about that. You just sat in your office and you said, this is how much it cost me, so I'm going to sell it for this plus 35% or whatever your markup is. Okay? Oblivious to what the end user wants or is willing to pay. And of course, when you suddenly realize you can't sell it, you don't have any options, because you never thought about reducing costs. You never thought about making things or coming up with better. You just said, this is how much it costs. Suddenly people say, okay, that's too expensive, we're not going to buy it. Now you have trouble. So lots of challenges happen because people cannot figure out why and how we can actually increase profit margins or sales if things start going bad. On the other hand, in target costing, you determine how much you think it should cost. And then you cascade it down. Given that I cannot sell it for more than this, how much should it cost me to make? So then you say, okay, well, no, I'm not going to buy that machine. I'm going to buy this machine. I'm not going to use that process. I'm going to use this process. So your whole approach is to meet that target, right? And that is a much, much better way to do things. And that automatically takes into account what the end user or the customer would be willing to pay. Yes.
So like in the target costing method, if the price is fixed in the development, in the concept generation stage itself, and what if we are not, the suppliers or the manufacturers are not able to meet the cost of the subsequent stages, won't the product be sold at a loss?
By you or by them?
Like by the suppliers, by the manufacturers.
But that's exactly it, right? So one of the things, this all relates with the lean way of doing things and all that, right? Pull systems versus push systems. The whole idea with pull systems and lean is so that you make the system lean just in time, so on and so forth, so that you identify where the waste was, right? And what is it that you need to fix. If you could say that there is no way I can make it for less than this, then you give up. At least you saved yourself so much trouble, right? Versus saying that I tried it and now suddenly I can't make it. And there's a lot of cases like that. Certain countries, when they start doing embargoes and tariffs on each other, they don't realize that, tariffs make sense in certain cases, but there is no way. Maybe you don't have the raw material, maybe you don't have the expertise. You could not make it for cheaper than what the other person is making. So just might as well let's buy it, right? So it even helps you identify that this is not going to be feasible ever, or helps you find ingenious ways of doing it. All right, so like I said, we cascade it down to individual operations. We reduce waste. We come up with technologies that will reduce cost, and then allows us to have a tight control over where all the expenses occur. And then you're well placed to ward off competition, right? If you are doing target costing and you're aggressive, and you imagine one manufacturer is doing target costing, another one's doing cost plus, whatever it costs. Obviously, the second one is going to be at a disadvantage because they're going to have higher costs, they're going to have wastage, and then they're going to have inefficient operations. Okay, so I mean, again, we talked quite a bit about. I'm sure you follow the U.S. automotive market through the 60s, 70s, 80s, 90s, 2000s, and then the Japanese versus U.S., and then the whole thing about lean, just in time, all that is actually has been shown to work many, many times in the automotive world. And I said last class that we are very close to automotive in Oakland University, Michigan. So we've actually been at the forefront of these challenges. Okay, and then alternative marketing strategies. Right? So sometimes we say, okay, well, so let's sell a product. Sometimes you'd say, well, we just lease it. So I don't know about here, but many places will not buy a copier or a photocopy machine. It's leased by Xerox or whoever makes it. Okay, so that company says, you don't own it. You just give us however much money per month. We'll bring it in. You can use it. When it goes back, we'll replace it. Goes bad, we'll replace it or we'll fix it. Right? So they're selling you a service versus the product itself. So leasing is obviously a model that you can explore sometimes. And we did some work in product take back and reuse, where we showed that leasing computers to end users may be actually a better way of not only just making money, but also reducing environmental impacts for products simultaneously. So alternative leasing is there. Razor and blade model. Have you heard of this one? So some shaving companies, they will sell you the razor for cheap, right? Knowing that razor fits only a certain kind of blade. And then now you are a repeat customer. You're going to keep buying the blade because that's the only blade that fits that razor. So they got you hooked. Some printer companies do that. They'll give you a printer for cheap, and then now you have to buy cartridges over and over again because, again, it'll only work with their printers.
Mosquito repellent companies.
Yeah. And what are the attributes of demand effects, product design, launch decisions? Time. You don't have to do everything right now. That's another thing people don't realize. Maybe you can just wait. Okay? So now I have some additional slides. We're just going to see how much time I have. How long have we done on this session? Do you know the time for the session we've had? Let me just quickly go over some of these things. If we don't cover it, we'll come back in the next class and do it, right? So concept generation and additional example. So actually, I want to address some of the things that you were saying. So I'll cover this in detail next class. Okay, so if I'm skipping things, don't mind me too much. So brainstorming is a technique. I want to just quickly go over here, right? So this is some concepts for a peeler, right? We didn't do a functional diagram of a peeler so far, okay? But here we're doing it. Vegetable goes in, material, energy goes in. So then, to your point that you were making offline, that can I add or subtract things from a functional diagram? Is it amenable to variations? That's the whole point, okay? So here I said, okay, in the functional diagram, we just hold and orient the vegetable, okay? You might think, what is the point of that? Well, guess what? You do it. You don't just take a vegetable and start peeling away here. You orient and hold it so that the surface that needs to be peeled gets peeled. Remove a layer of skin through relative motion, vegetable with a sharp edge. Okay. And examine whether fully peeled or not. See, that's something that people forget. I can hand a vegetable to pretty much anybody and they can peel it, no problems. But many times you don't think about this, that somewhere you have a vision system with a processing brain that tells you, hey, it's peeled. You don't keep peeling after you peeled it already, right? And you only peel the locations that you still have skin. So the idea is that this functional diagram drawn like this could have been drawn differently, where I completely dropped that element and didn't think about this. If I didn't think about this, I would make the same old dumb peeler that I've made for hundreds of years, right? I just look at it a little bit more closer. Hang on a second. What does it take? This is just the same block. Energy goes in, peeled or unpeeled vegetable goes in, because there's a loop here, right? You peel and you check, and you peel and you check, constantly checking. You don't just peel in one go. So it could be peeled or unpeeled. If it is already fully peeled, you stop. If it's not peeled, you continue. Okay, so what is the point of obsessing about this element? Decision making, but there was a decision that happened. There was a decision that you could make, or that was a decision that a computer can make. Okay, so the fact that I belabored this, now I can think about, hang on a second, I don't have to have a manual peeler. Like this company, right? So you could actually have a camera system with AI that checks whether you peeled or not. You could have a simple system like this, which has a limit switch, right? So it just rotates the potato and then it peels. And then when it hits the end, of course, everything is peeled. But this could be wasteful because it has to be circular. If you want to make it really more. So the thing is that just because we paid attention to that, now we know that we have to have a way, if you automate it, humans can be expected to know, yes, it's peeled or not, but a machine doesn't know. It'll keep peeling. So there's two solutions to that, to your point. I can have a mechanical solution that it peels, starts here, ends here as it's rotating, and that's peeled. Or it makes the most optimal motions and has a camera system with intelligence that peels it accordingly. So this is not a trivial step, and that's why I added it. And then now you can, if you kept it vague enough and abstract enough, you can come up with automated peelers as well. That was the point of this discussion. Okay. So I think that we can end today here, because I want to. If we want to start a topic that. Oh, thank you.